Okay, a titration curve is a graph of pH versus volume of titrant added. Okay, what the heck is a titrant? Well, in your burette, the solution in your burette is called the titrant, and the solution in the flask is called the anilate, also known as the sample. Okay. Okay, so the titrant is the solution in the burette, and the anilate is the solution in the flask. And it is your titrant is your known, and your anilate is your unknown. So as we drip titrant, and in this case, let's say that the titrant is NaOH, as we drip it into a flask containing the anilate, HCl, what's going to happen is we start with, sorry, I need to label my axes before I do anything else. This is going to be pH versus the volume of titrant added, and in this case, that's going to be the volume of NaOH added. And so initially, we have only HCl, okay? And so the pH is low. Now we start dripping in NaOH, and the pH goes up slowly. So the pH rises slowly. We have a shallow slope. And then all of a sudden what's going to happen is you're going to go to the tipping point, which is not called the tipping point. It is called the point where you switch from having an excess of acid to having an excess of base. And that is right at the equivalence point. Okay. And then we start having excess base, and then the pH levels off, and it goes up, but not too much. Okay. So does anybody remember what the equivalence point is? Equivalence point. No excess of either reactant. Yes, exactly. No excess of either, whoops, reactant. Another way of saying that, if you prefer, is the stoichiometry of the equation is perfectly satisfied. Okay, does anyone remember a second name for the equivalence point? Stoichiometric point, yes. Okay, excellent. All right, and tipping point is something that we're just kind of using. It's not an official term, okay? So don't use that on any questions. It's just it's very visual. It's like we tip over from being in the acid range to being in the base range, okay? And you can determine the volume of NaOH needed to get to the equivalence point. Maybe I should write that down below. From a titration curve, the volume of titrant, in this case, NaOH, needed to get to the equivalence point. Okay, so if we go back up to our graph, all you have to do is look for the vertical section and just drop a line down to your x-axis and read off the x-axis the volume of NaOH needed to get to the equivalence point. So this could be an alternate method that you use to find an equivalence point rather than using an indicator. You could have a graph. What you would do is you would stick a pH meter in your solution and you would measure the pH every few drips or so, and you would plot it on your graph and you could read that volume, okay? So the second thing you can do is you can determine, this would be read off x-axis at vertical part, vertical section of the curve. Second thing you can do is you can, from the titration, you can determine the pH at the equivalence point. Okay, so let's go back up to our graph. And we are going to find the midpoint of the vertical section. And that's going to give you the pH at the equivalence point. Okay, so you take your midpoint there and you just read right across. Okay, that is like a really slanted line. You would normally draw it straight across. Let's see if I can actually manage that. Let's see, okay. Yeah, somewhat better. Anyway, yeah, you're supposed to read straight across. So that's going to be the pH at the equivalence point is from that midpoint of the vertical. And in this case, because we have reacted NaOH with HCl and we have no excess of either, what is the pH at the equivalence point? 7, yeah. Okay, so that's our pH of 7. All right. And for a strong acid, strong base curve, that's pretty much it. Okay. It starts low, it finishes high, and the pH at the equivalence point is 7. You can find the volume, you can find the pH at the equivalence point. That's about it. Should we do the reverse, where we have a strong acid? So we will have a strong base, titrated by a strong acid. So our strong base then is our analate. It is our unknown. It is in the flask. And our strong acid is the titrant. It has a known concentration, and it is in the burette. So for example, we might have NaOH is titrated with HCl. So we are dripping the HCl into the NaOH. So where are we going to start? What is our pH going to be like at the beginning? Is it going to be high or is it going to be low? High, yeah, because we've got our NaOH in the flask. Okay. And our finishing pH is going to be low. Okay. And what do you think the shape will be like? A reverse S, yeah, absolutely. It's going to look just like the last one. Okay, I'm going to turn my tablet here so I can actually draw this. Let's see what I can do here. Da, 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 da. Okay, shallow slope, steep slope, shallow slope. And in the middle of that vertical section, that would be pH 7. And this volume right here is the volume of HCl needed to reach the equivalence point. Okay. So it's exactly like the last one, just reversed. Okay, pretty straightforward. So now what we're going to do is we're going to do one that's a little trickier. Okay, and it's going to involve some concepts that we have dealt with in the past. So it's going to involve a concept like hydrolysis. So let's take now a weak acid, titrated with a strong base. Okay. And before we do that, what I'm going to do is I'm just going to draw for a comparison sort of thing. This is going to be a strong acid, strong base titration. And then we are going to also, for comparison, draw the weak acid, strong base, titration. Okay. What goes on our x-axis? What goes on our x-axis? It is a volume. Is weak base, strong acid going to be the same? Yeah, except for it'll be upside down. Okay. Just like the other one was upside down. Okay. So yeah, it's going to be the volume of the strong base added. Okay. And we are starting with, so in our flask, we have our weak acid. Okay. Oh, and before we do that, I'm just going to quickly draw the strong acid, strong base one in black here. So we have this. And then we go up, 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 and then we go across. Okay. And that in the middle of that is going to be pH 7. It's going to be pH 7 right there. Okay. All right. Now I'm going to, in red now, start with my weak acid. Is the initial pH of the weak acid strong base titration higher, lower, or the same as that of the strong acid strong base titration? Is the initial pH of the weak acid strong base titration higher, lower, or the same as that of a strong acid strong base titration? Let's assume the concentrations are the same. Yeah, initially it is going to be higher. Why is it going to be higher? Yeah, it's weak. It's going to be less dissociated. Okay, only some of it is going to have come apart into H plus and A minus, as opposed to our strong acid, where we have, for example, HCl. It all comes apart into H plus and Cl minus. Okay, so our initial pH is going to be higher. Okay, there we go. Whoop. And there is a feature of this curve where there's a little hill at the beginning. Okay, so it's like a little scoop upwards, and then it kind of levels out. And then at the same volume, assuming that it's monoprotic, it will be at the same volume. It just follows the rest of the curve. Okay. So things you want to take note of here is that we have a hill at the beginning. Okay, once we get past that little hill, then we have a shallow slope, just like the strong acid, strong base. But you'll notice that the vertical section of the curve is higher, like on average is higher. And remember, if we are finding the pH at the equivalence point, it is the midpoint of the vertical section. So the pH at the equivalence point is going to be the midpoint of that vertical section. So if we follow that across here, let's say that could be a pH of, say, 9, for example. So the pH at the equivalence point is no longer 7. It's actually higher than 7. It's 9. Okay. So the pH at the equivalence point of a weak acid, strong base curve is, or actually, shouldn't write curve, I should write titration. Titration. Dear Lord, titration is greater than 7. Okay, it is still the midpoint of the vertical section. Okay. And why? Why is that? Let's take a look at an example here, okay? If we had our weak acid, let's call it CH3COOH, acetic acid, CH3COOH, okay? And we put it together with some NaOH. Our products would be NaCH3COO plus H2O. There's our salt, and there is our water. At the equivalence point, we have no excess acid and we have no excess base. So remember, at the equivalence point, the reactants are all gone. Okay, so I don't have any more CH3COOH, I have any more NaOH, all gone. What do I have left? At the equivalence point, what are the only two things that are in the beaker then at the equivalence point? The salt and the water, okay? So we have our salt and we have water. What can happen? Not always, but what can happen when a salt is dissolved in water? What process? Yeah. Hydrolysis. Okay, so back when we had our strong acid, strong base, we produced a salt that did not hydrolyze. But if we look at our salt here, NaCH3COO, we ask ourselves, who are those ions? Well, we have Na plus, and we have CH3COO minus, saltiness. Okay, do they hydrolyze? Do they react with water to produce H3O plus or OH minus? In other words, do they hydrolyze? Does sodium hydrolyze? No, it's not feel creepy, nor is it ammonium. Does acetate hydrolyze? Yes, almost all of our anions hydrolyze except those that are conjugates of strong acids. So our hydrolysis reaction then at the equivalence point would be CH3COO minus plus H2O. CH3COO minus acts as a base and accepts a proton to become CH3COOH plus OH minus. Okay, and look what we have done. We have produced hydroxide ions. And hydroxide ions means that this is going to be a basic solution, which means the pH is going to be greater than 7. So hydrolysis is the reason that we have a pH greater than 7 at the equivalence point for a weak acid, strong base titration. Okay. And I think that would be a good point to leave it at for today. So you've just sort of taken a look at the curve of a weak acid, strong base. Okay, so just to quickly review the differences. Okay, so we have this hill at the beginning when we have a weak acid in our flask. And the vertical section is on average higher, which means that the pH at the equivalence point is greater than 7. And why is it greater than 7? It's greater than 7 because you have made a salt, but that salt can hydrolyze, and it will be the anion that hydrolyzes, and so you'll end up with basic hydrolysis. Okay, so that would be due to anion hydrolysis. And that's a lot on that one little graph. We will go over this again next time because that was a lot to do just in one little session.